Welcome to Lecture 12 in GRA 6036. This is the last lecture for this semester, and you'll get the exam in a few days. So today I'll do exercise 1.5 from the More Math and Some R exercise set that I've put out on It's Learning with the solutions to all the exercises. And I strongly advise you to do all these exercises before the exam. So there's also a solution to exercise 1.5, but since it is important for the intuition behind p-values, I'll do it here. So this is then exercise 1.5, which is called Is My Coin Fair? So the point is that we have a coin, and we think it is fair, but when we're not sure, and we want to use statistics to test whether or not we should think that the coin is fair. So by a fair coin, we mean a coin where the probability of getting heads is the same as the probability of the coin landing tails, equal to 1/2. So to translate what we want to do into hypothesis, our null hypothesis will be that, well, we do think that our coin is fair, so our null hypothesis is fair coin, while the alternative hypothesis is that it's not fair. So it's difficult to translate such a hypothesis into symbols. So let's introduce a symbol, P. So we'll let P be the probability of getting heads. And then 1 minus P is the probability of getting tails. And if we translate these hypotheses using, if we express these hypotheses using this symbol, this means that our null hypothesis is that P is equal to 1/2. That's a null hypothesis, versus the alternative that it is not equal to 1/2, that it's different from 1/2. So this is an unfair coin, this is a fair coin. Okay, so to test this hypothesis, we need data. And an easy way to get data here is to toss the coin a few times and then record the outcomes. So let's suppose that we toss our coin 6 times, and on the first toss we get heads, on the second toss we get heads, on the third toss we get heads, on the fourth we get the tail, then on the fifth heads, and on the sixth heads. So this is, and then we stop tossing. This is all we managed to do, and so this is our data. Now we want to use these data points, these 6 data points, to test this hypothesis. And the reasoning here is that if we get data that is strange, under the assumption that the null hypothesis is true, then we might no longer believe in the null hypothesis. So here this seems a bit strange, because this is it's a fair coin, and so we would sort of expect that we will get 50-50 heads and tails, and here there's only 1 tail among the 6 tosses. So this sequence, is a bit strange under the assumption that our coin is fair. But the question we want to use statistics to answer is it strange enough for us to stop believing that the null hypothesis is true? So let's first compute the probability of getting this sequence of data under the assumption that the null hypothesis is true. So assuming that P equals 1/2, then the probability of getting a head is 1/2. So that's the first toss. On the second, I mean, and these are independent, so you can multiply them. On the second, that also has probability 1/2. This is probability 1/2. The tails has probability 1/2. 1/2. 1/2. 1, 2, 3, 4, 5, 6. So we get 1/2 to the power of 6, which is 1/64. So this is then the probability of getting the sequence that we got. And of course 1/64 is not a very big number. So in a sense, I mean, this sequence is strange because well, this is a small number, so we're sort of surprised to get this sequence. But we can't use this probability to reject the null hypothesis. Well, why not? Well, because assuming that the null hypothesis is true, any sequence of 6 tosses has this probability. So let's look at one other sequence that would not be, well, surprising in a sense under the null hypothesis, namely the sequence where we get heads, tails, heads, tails, heads, tails. So here we have 3 heads and 3 tails, which is sort of what you expect from a fair coin. But the probability of getting this sequence is, so the heads is 1/2, 1/2, 1/2, 1/2, 1/2, and 1/2, which is 2/6 equals 1/64. So we see that this sequence that appeared strange and the sequence that is not so strange, they have the same probability. So obviously we can't use this probability to say something about the null hypothesis. So we need to ask a different question. So the question we will ask is a more it's a bit more complicated one. Is the question of what is the probability of getting a sequence that is just as surprising as this one, or even more surprising under assumption that the null hypothesis is true. So first we have to agree on what are sequences that are just as surprising as this sequence under assumption that the null hypothesis is true. So of course all other sequences, we would be sort of just as surprised by all other sequences that only contained one tail among the 6 tosses. So that means that we'll be just as surprised by tails, heads, 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 tails, heads, 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 and so on. The last one, and then heads, 1, 2, 3, 4, 5. So all these sequences would surprise us just as much as this sequence. And of course, among these sequences, there is 1, 2, 3, 4, 5. There are 6 such sequences. But we would also be equally surprised by all the sequences where we got one head and all the remaining 5 were tails. So this means that we will be just as surprised by sequences of this form: 1, 2, 3, 4, 5. One, 2, 3, 4, 5. So these sequences, can be argued, would surprise us just as much as this sequence if we really think that the null hypothesis is true. There are 6 such sequences. Then we go to then we'll also need to think about the sequences that would be even more surprising than the actual sequence, assuming that the null hypothesis is true. And those are the 2 sequences. So now go to the next page. Those are the 2 sequences where we get tail, 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 and heads, 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 heads. 1, 2, 3, 4, 5, 6 heads. So there are 2 such sequences that are more surprising. 2 more surprising sequences. So if we add all these, if we add the just as surprising sequences, we add 6 plus 6. So these are the just as surprising plus the more surprising. We get 14. So there are 14 sequences that will surprise us just as much or more under the assumption that the null hypothesis is true. So that is important, assuming h naught p equals 1/2 is true. So then we can compute the probability of getting a sequence that is just as surprising or even more surprising under assumption that the null hypothesis is true. So, and that is, so let's write that down. So we have the probability of getting a sequence, getting a sequence of 6 tosses that is just as or even more surprising than the one we got. And I remind you that the sequence we did get is the sequence right here with our data. Okay, so this is then under assumption that h naught is true. That's a long sentence into the parenthesis. Well, we know now that there are 14 such sequences, and we have to divide that by the total number of possible sequences that you can that you can get when doing when tossing a coin 6 times. And well, so how should we count the possible number of sequences? Well, you can draw you can start by drawing a tree. So like this is the first toss, you get heads or tails. You move on to the second, you get tails, heads. You get tails, heads, and so on. And then if you draw this thing all the way out and you count up all the end nodes in the tree, you get to 64. The same way, another way to think about this is that you have say you are at a restaurant where there is a 6-course dinner, and for each meal you can, or for each of the courses, you can choose between 2 different dishes. So then how many different experiences can you have at this restaurant? Well, so you either choose this starter or that starter, then you move on to the second course, you choose this dish or that dish, etc. You get to 64 different experiences at this restaurant. Okay. Well, so this is then the probability 14/64 or 7/32, which is 0.21875. So I'm cheating here, I've computed this probability already. Well, so this is then the probability we are going to use to say something about the null hypothesis of the coin being fair. And this probability is also what we refer to as a p-value. So, right, this is a p-value. Because a p-value is, what I've been saying a few times now, the probability of getting the data you got, or something more extreme or more surprising, under assumption that the null hypothesis is true. And that probability for 6 coin tosses is what we computed right here. So this is a p-value. And this, so this is the same thing that you look at when you do your linear regression models in R, your LM function. You get a table, and then the last column is a column of p-values. Well, then you look at values of this type. So to make our decision now, we must have chosen, preferably before we conducted the experiments, a significance level, which means a significance level is the probability. So a significance level. So let's see. Significance level. So it's the probability of rejecting, the probability, or the maximal probability of rejecting a null hypothesis when the null hypothesis is true. So of course that's not something you want to do. I mean, if your coin is fair, you want to have a test that, well, you preferably want to continue to believe that it is fair if in reality it is fair, I mean, after having done your tests. So if you commit an error, a so-called type 1 error, if you reject a true null hypothesis. And that probability we want to control, and we want to make it small. We can't really make it 0. I mean, and well, we can't really make it 0 without, well, we can't make it 0 if we say that we never reject the null hypothesis, but then we will never be able to detect an unfair coin neither. So, I mean, so the significance level is the sort of the probability of rejecting through H naught. And we want that probability to be smaller than or equal to some number. And that number, alpha, is commonly chosen to be 0.05. So now, this means that for us to reject the null hypothesis here, I mean, to stop believing that we have a fair coin, this number, this probability, must be smaller than our significance level. Well, it is not, so we do not reject the null hypothesis based on the sequence of 6 coin tosses that we got.